Well, good morning. I'm back again with my latest auction score piece. Slowly working my way through the list of things. Now, this one is similar to things that you've seen before on the channel. And in fact, I've replaced the functionality of this. But I saw this in the auctions there, and it's just in pristine condition. And it's just such a classic device that I wanted to buy it just for the sheer enjoyment of collecting it. And so this is, the original 4 Series 435B power meter. And as you can see, this is in, for something that's 60 years old that I have not touched up at all. This is exactly how I got it out of the packaging from the vendor. It's just pristine for its age. Basically, what these things are is these are a power meter that's designed to read RF power, and it was jointly built with the 8400 series, though the 8480 series of power sensors. And so basically you would connect the power sensor to here, and in fact I have a power sensor here. This is a little 82, let me turn that around. This is a little 8482A power sensor. This is a guy that'll run from something like 10 megahertz all the way up to 4 and a bit gigahertz. The 8481 will go up to, I think, 18. But these little thermocouple sensors that were removed from the 432s, which is the other meter prior to this that used a thermistor. These used a thermocouple. And the basic idea is that you put RF power into the thermocouple that creates a DC offset that can be then read by this meter. And you can calibrate the whole thing. So on the front here, what we see is the sensor connection. We see a 0 button and a calibration factor. How these, and I've talked about this in my previous meters, is these sensors will react differently depending upon what frequency you're at. And you can see here there's a list of frequencies with a calibration factor. And so that set of calibration factors you can just check in here in a very coarse way. Basically it's 1%, so it's 100, 99, or so on. And as you can see on this guy here, I started 100 megahertz, I started 10 megahertz, and it's 98.7, and then it stays pretty much in the 98s all the way to 300 megahertz, and then it drops down to, so that'd be the 99 button that I'd have it on. And then it drops down to the 98 button basically for up until the end of 2 megahertz, and then steps down again a little bit. So they're much more granular, whereas in the digital meters you have extra resolution to put that calibration factor in. So you'd set that calibration with the sensor, and then once you're there you'd press the 0 button, and this creates an auto feedback circuit that basically reads the current value of the bridges and then sends it back into the system and basically zeroes out everything so that you're ready to go and read. This then tells the underlying mechanics what power range we're going to be in when we're reading, so that this way the meter can give an accurate reading. And then because all of these things are basically reference measures, you need to have a power reference, and these are very accurate 50 megahertz, 0 dBm, or 1 milliwatt power reference. And so I can attach this to the power reference here and set that reference point. Now I know that what 1 milliwatt is, so now I can go read microwatts or watts or so on, depending upon the sensor that I have. So that's the basic operation. You can see it here. What I'm going to go do now is just take the covers off and let's take a look inside. It just occurred to me that I didn't show you the back of the instrument. Here's the back. Obviously the power cord goes in multi-voltage. it has a very simple switch to turn the power reference on and off. Typically, you don't want to be running those power references 24/7, so you want to give it a chance to warm up and then do your reference check, and then switch it off. They then have what was very typical of instruments of the era, two outputs here: a recorder output and an RF blanking output. And the recorder output basically puts out a 0 to 1 DC, 1 volt DC value that reflects the meter deflection at the front of the unit. And so you could plug that into other multimeters. You could plug it into a strip chart printer, which just printed basically a strip, and it sort of like the classic EKG things you see from medical shows. And then you have a rear sensor output and RF blanking output. Just had to duck away for a second. Just to come back, just to finish off the back here, there's an option that you could get. I think it's 003, which would let you put the power sensor input that was on the front of the device, this guy here. You could have it in the back of the unit, and you would do that in conjunction with the RF blanking output normally in a production or rack sort of mount world, because what the RF blanking output does is when you press the 0 key, you get a signal out here which enables you to disconnect automatically the RF signal that's coming into the unit during the zeroing process. So you don't want the signal input or a live signal being read when you zero. So you can automatically turn that off, and it makes for the process stuff much better. So before we go further into this, I wanted to show you something that I've had these meters before, and I have never seen one that actually came with the little rings. There are a set of rings that exist, and let me put them down here and zoom in so that you can get a better view of them. These rings let you set the ranges, and they're designed for the specific sensor that you're using. And so depending upon which sensor you use, you're going to put the appropriate ring on, and that gives you on the front of the unit, that where you set the, I don't know if we dropped it in there, you might not be able to see it. On the front of the unit where you set the range, you now have the appropriate information there. I've never seen one of these that actually had the rings still on them. They usually get lost or they're damaged, and they're just in perfect condition. This is this little 8482A will go from I don't think it's actually written on here. I think it's like minus 30 dBm to plus 20. So we would go and use this ring here, which is the 20 to 25 range. This would be for something like an 84 or 81D or something where that would be a minus 20 to minus 70 range sensor. And then on the other side would be the 8481Ds, 8481, 84D. Anyway, the one that is from 0 dBm or just down below 0 dBm up to 44. It comes with a great honking heatsink on the sensor so that it can dissipate the power that is coming in. Anyway, I just thought I'd show you that before we went any further. Let me get that right one again, and that is this guy here. And we'll put these back onto the switch there with the appropriate range, so from 20 to minus 25, because we'll be using that sensor a little later. And that's sort of how you look at it. Anyway, I've taken off all of the the side panels. And the side panels, and I just love this, how HP used to do this on their equipment. They had this sort of vinyl textured coating, and it was consistent. And I just love the feel of that, that cases. And the new cases, while they're not bad, or they're very well designed instruments or so on, they're just not the same. Anyway, they use this common frame. This is a very common construction methodology for instruments of this era from HP, which is this cast aluminium frame. And you can see basically that there's an awful lot of space in here. And the reason there's an awful lot of space in here is not only do you need a certain level of form to enable you to actually go and have the meter being able to be read into it, so it's going to define a certain factor in terms of the width and the height of the controls and so on. But you could also get an option that made this thing completely battery powered, and you would drop the battery in here. I don't know, you might have seen my other video just on the battery, but it'd be something like this. Not this particular battery, because clearly this battery is too long. But the actual construction of the battery that goes in here is very, very similar. It's this cell model, and so it was probably about that sort of length, and it would fit in that hole there. And then there'd be a metal case to hold it. Anyway, that's why there's this open space here in the boards right over to the side. If we look in a bit closer, this is the 50 megahertz reference, the 0 dBm 50 megahertz reference. And you can see this control here is what you use to set the level. And then on the control, I'm going to see if we can get a better view of that. There, inside this can here are some settings that will control the oscillation and the frequency that it will oscillate on. But that basically exists just solely to run this power reference here and to give you that known standard. And if you tune these in properly with the NIST gear, and that's the 432 with the 478 thermistor, you can get these to 0.7% accuracy on these meters here on the reference, which gives you, in the RF terms, in terms of the era and the power meters, a very, very accurate ability to measure powers across a wide range. Anyway, that's that guy there. Let's have a look at the side here. Now, what you've got on the side here is this circuitry is basically a chopper amplifier with multiple stages at the end, in the middle, before it pumps out the final value of the meter. So basically, if you've seen a 419 or looked at how the Fluke or HP gear of this era was built, it's very hard to make a DC amplifier that will be very accurate and very linear and so on, and it was much easier to make an AC amplifier. So what they would do is they would take a DC signal and they would run it through a chopper, and the chopper would cut the signal up and basically create an AC signal out of the DC value. Then they could feed that through the amplifier stages and very accurately amplify that AC signal. And then at the end of it, they demodulate it and come out with the final DC value. Now, this is a bit of a hybrid model. What they do is they take the signal in, and it's a 220 hertz chopping that occurs from the sample. And the sensor and the meter form sort of this hybrid chopper operational amplifier. And so they bring in that, and then they chop it and create the AC signal. And then there are 3 actual stages of amplifier on this board here as you go through from first, second, third stage in the AC amplification. And then from there, once you're done with that, then it's demodulated and put through a DC amplifier before it's finally presented on the meter display. And anyway, this is the main board where all of that happens. And you can see the layout. This is looks like it's actually a fairly modern version of this meter. So that would probably explain the pristine condition that it's in. We have some TO92 packages in there that you can see, some what is it, TO36s, TO18s. You know, the original electrolytics, you can see that the layout is still very much rectangular and, you know, 90 degrees and that. There's still starting to get a little bit of angular layout in terms of the tracks. And the board plugs into a board edge connector that really comes into the bottom here and is used to basically just simply share the stuff around and act like a holder effectively to connect it. It's not really sort of creating motherboard type model. It really is a motherboard, but in the classic motherboard idea where it really was just a back plane, I guess. And so that's pretty much what this is. And you see this is a reasonably later version because in the earlier ones, you know, there was no integrated circuits, there was no you know, flex ribbon cable and dip sockets and things like that. So at some point they've done a little renovation to the underlying plane here to update it to give it a little bit more functionality. I'd have to go away and have a look and see what that IC is. DG201ACJ. Never heard of it before, so I don't know what it actually does, but there's a couple of them on there. And you can see that the board that's holding the, if we look in there, you can see the switches are much more modern construction instead of the classic board with copper trace and you know, the contacts rubbing across it. This is actually you know, a brass or a copper plate inside a plastic housing, and should be much more reliable in terms of the switch contacts themselves. Anyway, that's basically all there is to the meter. There's really not a lot here, and you can see this through it's a single-sided board construction and so on. So let's reassemble it and see if it works. Alright, so when you get these things, because of the age of the instruments, you don't really know whether they're going to work or whether it's going to be, you know, is there any problems or so on. And so before you go plugging in expensive things like these sensors are, you know, several $100s, you know, you want to make sure that it's doing a couple of, doing some things right. And so the first thing that, you know, you want to do is you want to make sure that the output of here should have no DC value on it at all. So what I'm going to go do is take my little Rigol meter, you know, and we'll screw in a little adapter from N type to B and C, and then we'll put the Rigol meter on there, and we'll turn the power reference on, and we'll look to see if there's any DC out. Alright, so there's no direct DC out, which is good because if you take that output and you start feeding it into some other systems without knowing whether there's DC in it, some things can be very, very sensitive to the amount of DC voltage that is coming in, and it's not unheard of that these things will have some form of DC offset problem in their output. Okay, so now that we've seen that it doesn't have any DC output value, we can now take a look and see what the actual power reference looks like. So let me set up for that. This is another piece of kit that I scored in one of the DoD auctions, and this is sort of part of you know, why I end up with a bunch of random stuff, because I really wanted this guy. This is an 8714C RF network analyzer, and I'm not going to spend any time on this. I'll do a separate video on the RF network analyzer. But what it does is it enables me to do some things such as measure components and get an idea of exactly how they react across frequency. So what I have here is I have just two cables hooked up, just their N-type cables with a female-to-female adapter. So I'm just going to hook those in together. And we should basically see when it's all said and done, you know, this is RG316 and the N-type connectors are good. basically a flat line across there from 0 to 3 gigahertz. Now, the reason I'm doing this is that I want to check, I want to get an idea of what this particular attenuator is going to give us, because you know, the RF meter's reference may be driving a very, very high level of signal, and so before I attach a sensor to it, I want to make sure that it's not actually driving something insanely high. And now I don't have an RF voltmeter here that I could just plug straight in and measure that. So what I need to do is to put in a bit of attenuation that I know, and then I can look back. And so this is a 10 dB attenuator, and what I can see here is this. So I'm just going to go in and cal, and then we'll normalize it. We can see a straight line. Now let me actually go in and we'll set the stop frequency to be 75 megahertz, because this is a 50 megahertz receiver, and you can see now we've got some additional stuff in there. So let me normalize that again. Okay, now what I'm going to do is I'm going to take this apart, and we can see this, and I'm just going to slot in this tech scan. These are nice, well-made little attenuators. So we'll slot in this little tech scan attenuator, and now when I do that, you can see that now that all the context in there, it's basically minus 10 dB. And so when I go in and I select marker, and I can scroll this up to the 50 megahertz line, and I'm going to get roughly 10 dB down. So what I can do is I can now go and put this in line with my other sensor that I'm going to go use to see whether or not this guy is accurate. Okay, this is the 8902A measuring receiver that you've seen in a previous video, and we're going to go use it to measure the RF output on the reference for the 435B. So the first thing that I need to do is calibrate my sensor here. And now this is an 11, let me get that straight for you so you can see it. This is an 11722A sensor module. And basically what it is it's a switch to tell the sensor to send the RF signal out one of these two cables. It's a 10 dB attenuator, a 8482A sensor, and then a straight through cable in there. So it's basically the same as my RF power meters, but with some additional functionality. So what I need to do is I need to calibrate and zero the power meter, and the 8902 has its own reference there. So let me just drop that in, go to RF power, and then once we get, we'll see a value come up here. That's great. I can hit 0. The unit will now zero out those bridges, just like the 0 on the 437 and the other items. And so that's all set. And then now I can go in and I can hit calibrate, and I should see about a milliwatt. Damn, it's very close to a milliwatt. So if we go put that in dBm, it's basically going to give me that. So let me accept that as the calibration value. And there we go. We're now all set, and I can turn calibration off, and we can go use this to measure the output. Okay, so let's take our attenuator, drop it onto the receiver. Let's take our little measuring receiver, the 11722A, and let's drop it onto the receiver as well. And we'll just keep doing that until it's finger tight. That seems to be pretty good. Okay, now I'm going to turn the receiver on, and I'm going to turn the power reference on. Now, when I turn the power reference on, you can see that I'm getting about minus 10 dB, which is what I would expect with that item there. So let's turn the power reference off, and let's unplug the, well, actually I don't even need to do that because I can leave that on, turn the power reference back on, and I can push the button up here to go to frequency, and you would have heard the little click. And if I look at the frequency, it is 49.8694 megahertz, which is well within spec. It's 50 megahertz plus or minus 5 megahertz, they really say, in terms of the frequency output. The most important thing is not so much the frequency, but that actual power. It's like 1 milliwatt plus or minus 0.07% is the accuracy there. Okay, looks like we've got a good reference. Okay, so let's hook in the sensor. We'll plug in that cable down here and just screw that in through the sensor cable in nice and tight. And we'll set our range to 1 milliwatt. I have a 1 milliwatt, I have the sensor in there. And you know, if I turn the system on, I'm going to turn the reference off. Turn the system on, you'll see that we're at 0. My calibration factor is 99%, so I set that. Let's hit 0, and you'll see the needle just barely moves, and it moves down to 0, and then once it's there I can let go of the 0 button. And when I turn on the meter, you'll see that I'm reading well and truly above 1 there. Let's go and set that range to 3 and see what it thinks I'm actually reading. So what it thinks that I'm reading is basically 1.5 dBm. So let's go now. I should be able to use the cal adjust item, and let's bring that back in. So I should be able to turn that down. So bring that into 1 milliwatt. So now that we're back there, I can keep coming down, and I think that's pretty good. So if I go to 3, you'll see that it's there. If I go to 10, you'll see that it's, you know, at 1 effectively across the top there. You know, it's at 0 over here, and so I can do 0 dBm and an offset. So on the 10 dBm range, that would be 10 dBm, and down here you can see that I'm reading minus 10 dBm, so it's saying that I'm off there by a bit. So let's go back to that value, and now I'm going to go hook this up to my 8657B signal generator. Alright, so I have this hooked up to my 8657B, and I have it set for 50 megahertz, so I don't need to touch the cal factor. Let me turn the RF on, and we can see that yep, it's about 1 dB, which is pretty much what I have set here. So let me do amplitude increment set. We're going to do 1 dBm, and so basically I'm just going to step it down by 1 dBm, and you'll see it now at minus 1 dBm, and you can see the minus 1, minus 2, 3, 4, 5, 6, 7, and so on, down to minus 10 there. And if I went down to minus 5, you'll see the range come across, and then I can go down further. You know, now I'm at minus 13 dB roughly. So, you know, the 8657 isn't 100% accurate in terms of its output level, and this thing I haven't done a range calibration on it, but overall it looks like it works out pretty well. Now let's go and step up the frequency a bit, And let me go back and set it back to 0 dB to 1 dBm, roughly. And I'm going to set this for 2 gigahertz. So let's set this for 2 gigahertz. And you'll see that the range has changed there, and now I need to step down calibration a bit. Well, it's unclear, you know, my actual 8067 may not be particularly accurate over the ranges. I haven't actually gotten around to calibrating it yet to go through all the output settings. But, you know, if I now step down by, you know, the 1 dB, you can see basically I'm still getting that same thing. So overall, looks like a pretty good score. It's a working meter. I hope this gave you some insight into how the 435B meter series works, and that you enjoyed the video. Catch you later. Bye.